one, when you're drawing this, I would highly recommend that you make it a large drawing, because small drawings will be harder to draw the forces. So let's just have an incline, like so. Right? Draw a block. My favorite drawing is a rectangle. Then we draw a center of mass. We're going to draw our forces from, right? So, question 1. What are the forces acting on the block? And remember, you can't tell me what to do in it, don't say it. Yeah, what are we going to say? Gravity, right? Definitely. Now, question, where does gravity point? Down. Great. Straight down. Right? Goes pretty straight down. Great. And we label it FG. Where's the gravity? What else do we have acting on the block? The normal force, right? But it's tricky, right? The normal force is a little tricky because what we got to do is, can you sit over in front of her? Yeah, here's some front of it. Sorry. It's tricky because the normal force is not pointing directly up, right? What is a normal force? Can anybody just give me like a quick summary? What is a normal force?
Something that prevents the block from falling down.
Something that prevents the block from falling down. Yes? Yeah, it's like a responding force, right? And how do we define the direction that this responding force points? Yeah, right, so the normal force a responding force from a surface onto an object that acts perpendicular and away from the surface. Right, that is what the normal force is. So how do we draw it when the surface is tilted? Well, I like to use a little model. I use like markers, right? So if I have markers, right, and I use my eye and pretend that's my surface, right? If I put the marker, right, on the surface, this is like the normal force when the surface is flat, right? Markers point up, surface is flat, everything's cool, right? And it agrees with what we said before, the normal force points up in that situation. So if we want to understand what happens to the normal force, let's just look at what happens to the markers when I tilt the surface, right? So if I tilt the surface, what happens to the directions that the markers point? Changes. How does it change? Yeah, so as the surface tilts, the normal force also tilts, right? So all we got to do is make sure that when we're drawing the normal force, that it's tilted along perpendicular to the surface. So what I do is I create like a little dashed line down the incline, which is parallel to the surface, so I can easily see where I'm going to draw my normal force. And then I draw like an arrow that comes from the center of mass out towards 90. Right? So you line up your protractor with the parallel line to the surface. Protractor is helpful. And then we draw an arrow. Like so. Label this guy. That's it. All the forces we have to deal with here. Yeah. No, it's frictionless. Keep it simple. Friction, no friction. So in our start on our first analysis, we're not going to deal with friction. We'll deal with friction later on, but just to understand how it works, we're assuming no friction, so like a frictionless surface. Yeah.
So how do you like use the constants?
Yeah, it's not
So
what
if there is friction,
Yeah, we're not dealing with friction yet. We're going to deal with friction when we get to it. I don't want to handle that right now. Right? Let's do it. Do the simple stuff first. So that's it. There's only two forces in this case: the normal force and the gravitational force. Right? But this doesn't quite explain our problem here. The problem is why does the thing accelerate? Why does a block accelerate down this? I mean, like, look, I can just, now this isn't perfect because obviously this is friction, right? But if I take the block, I put it on the incline, it accelerates, right? So our challenge here is that these guys aren't all aligned in the same set of axes, right? Kind of like, remember when we fired projectiles, right? And I said, let's say it was like a 40 meter per second projectile. And let's say the angle was 20 degrees just for kicks, right? Could I, if I want to figure out how high the projectile goes, could I use 40 meters per second as my initial velocity? To figure out how high the thing goes. No. Why not? Why can't I use 40 meters per second to find how high it goes? Just 40 by itself. Yes?
because it's not 40 meters per second in the y direction.
Right, it doesn't point 40 meters per second in the y direction. It's like the overall picture, which is kind of the problem here. This force is the overall weight of the object, but it's not telling me how much of this weight is being distributed along the direction of motion and how much of this weight is pushing into the incline, right? So in order to solve this problem, what we need to do is we need to break the force into pieces, right? Resolve it into components. Never remind me, what does it mean to resolve a vector into components? We did this back when we did vectors, projectile motion, we had to do this. What does it mean to resolve the force into components? Yeah? Yeah, like x and y, right? In this case, I had a vx, right? That'd be like vx. And then there was a vertical part that we would call dy, right? Nothing too crazy about that. Now the challenge here is that x and y is not very convenient, right? In this picture, y is like that, and x is like that, but that's not too good, right? Because it's not where the thing's going. This thing's not going technically in the horizontal direction, right? It's like going down the incline. So instead of using x and y, all I'm going to do is I'm just going to kind of like take the whole axis, just go like this, right? Like bend it. So instead of having an axis that's like vertical and horizontal, I'm going to create an axis system that works with the system that I'm in question, right? So instead of like up and down, I'm going to draw an axis that's like this, and I'm going to call that the parallel axis to incline axis. And then I'm going to draw a perpendicular one. Like this, and this will help simplify our problem. Because now what I can do is, since this is already, we can kind of just break gravity into the two pieces that resolve into these two directions. So I'll use two colors to help simplify this, right? I can think of gravity not just as one force, much like thinking of velocity as two pieces. I can think of gravity as two pieces, having a piece directed into the incline, and I'm going to call this the FG perpendicular piece to line up with our perpendicular axis. And then I'm going to have another piece that's going like it's tricky to do. You have to really be careful. Right. So I have a piece going down the incline like this. We call that FG parallel. That looks better, I think. So, right, we've got two pieces. We got down the incline piece and we have into the incline piece. And now we can understand why the block accelerates. Why is the block accelerating? Why is the block accelerating? What do we need to have acceleration? Anyway, yes?
There's gravity pulling it down the hill.
Right. And is there any force balancing that force? Is there any force balancing the down the hill force? No, right? In this axis, my perpendicular axis, they're balanced. Oh, in fact, can we really make a relationship? What's the relationship between the normal force and the perpendicular force? They got to be equal, right? Because they're balancing each other out. This normal force is balancing out that inward pressure from gravity in that direction. So we can write Fn equals Fg perpendicular, right? And if that's true, right, we then know that this guy, since there's nobody balancing him out, the acceleration down the incline is going to come from our net force, the unbalanced force, divided by the mass. So what's the accelerate? The mass is easy. Which force is unbalanced in our diagram? Which force doesn't have another arrow canceling it out? Ft parallel, right? Ft parallel. Okay? Now, great. Problem solved, right? That's the easy part. Question so far. Take a minute. Make sure you clearly understand the arrows and how they're related, right? These two forces are not new forces. These two forces are not new forces. They're just parts of the weight, right? So make sure you understand that. They're not different forces. They're parts of the weight. So now what we need is we need a relationship that allows them to connect. Yes? Yes. So what I do is I broke gravity into helpful pieces that go in the direction of the motion and go push it into the incline. So you can figure out the normal force and the unbalanced force. Yes? Huh? Yeah, you could use a resultant vector, but it's better to kind of show, because if you add this and this, it'll be the same thing, right? That's because this guy's equal and opposite. Huh? You have to draw all of them? If you're trying to show the two components. You know, you don't need the dash lines. I put the dash lines in there just to keep track of, the points of box, right? But you need to know that gravity can be separated into two components. One into the block, Ft perpendicular.
I didn't go to the line, but I go like the line even the at point of at the at point of at parallel.
Oh, you mean from like this, like that?
Yeah.
Like a downward line?
Yeah,
Yeah, well, you got to be careful. That's assuming that it's only gravity that you're dealing with. If you had another force, you might have more problems. So it's better to resolve the vectors into components. That's what I would say. I'm not going to test you on having to replicate this. But you need to understand this in order to be able to understand how the block accelerates down the incline. Okay? Now, this is the key relationship, but it still doesn't explain how we can calculate it, right? So in order to calculate, we need to do a little geometry, right? So what I'm going to do, instead of drawing it like this, because I'm not going to overlay it on top of it, it gets a little confusing. I'm going to move the vectors a little bit. Remember, we're always allowed to translate vectors, like move them from one spot to another spot, as long as we keep like the lengths the same, the direction the same, right? Remember doing this before? Like moving vectors, right? So I'm just going to redraw the incline again, and I'm not doing exactly perfectly to scale, but you'll get the sense of how this is going to work. So I'm just going to forget the box for a second. I'm just going to move. I'm going to make like a parallel force down the incline with colors. Okay, so I'm going to have the parallel force, and I'm put him along the axis like that. Gravity, I'm going to take a downward arrow. Gravity is going to go directly down, right, Fg. into the incline. Okay? So what I want to do now is I want to create a relationship. See, what does this thing rely on in terms of the downward force, right? What does this force depend on within the problem? What do you think, Thomas? The red line. What does the red line depend on? Right, but gravity's not going to change the block. What can I change about the incline to make it push harder down the incline? Yeah, I can make it steeper or less steeper, right? If I have it like this, it's going to be different than if I drop it like that, right? So we know there's a dependency between these forces and the angle, right? The angle of the incline. So what we want to do is set up a geometric relationship between the angle of the incline and these forces that allow us to come up with an equation that allows us to calculate these two parts, right? So I'll call this angle down here theta. I'm going to call this angle up here a weird angle called phi. I'm going to call that angle x. And if this is perpendicular with the bottom, how much does that have to be? 90 degrees. Right? So far so good? So I can write two equations. I can write one for the first triangle, right? If this is theta, this is 90, this is phi. I can write theta plus phi plus 90. What does that got to equal? What those three angles have to equal to? 180. And I can subtract 90 from both sides, not change anything. So I get theta plus phi is equal to 90. Everybody okay with that? And if we look over here, this force, this green line was the FG perpendicular. This red line was FG parallel. So what's the angle between the perpendicular and the parallel? 90, because that's the definition of perpendicular, is 90, right? So we know from here to here, this angle is 90. So that we can write then, well, these two angles add up to 90. We can write x plus phi equals 90. Anybody notice anything from those two equations? Some relationship. Rebecca? Maybe I'll read. Maybe let's rewrite this a little bit, right? I know theta plus phi equals 90, and x plus phi equals 90. So theta equals 90 minus phi, and x equals 90 minus phi. If theta equals 90 minus phi, and x equals 90 minus phi, nada. Theta equals x. So, with that geometric relationship, we can then say, well, if this is theta, then the angle up here between the perpendicular and the weight is just also theta. And that's critical for us to do the next step. Take a minute, soak it up. Absorb, process. Questions? Any questions so far? Great. Breathe out. One more triangle. You get it? Great. Yeah. One more triangle, if we haven't done enough triangles. Look, what I find, it's always better to separate these pieces out into different diagrams, because if I tried putting that on top of this, you would mix all our lines up and you get yourself confused real quick. So what I'm going to do is I'm going to do one more time. I'm going to draw the same thing I did over there, but I'm just going to move them a little bit. We know we got a downward force Fg, right? And I know that this force, the green force, is like perpendicular. Right? That's FG perpendicular. Right? And instead of drawing the force up there, I'm going to bring it down to the bottom and connect this line down here, make that FG parallel. Everybody okay with all that? Great. Hey, how much is this top angle over here? What is it? It's theta, right? And if it's a right triangle, we can label the sides of the right triangle. This guy is the one that's across from me, so I might call it the opposite side. This one is the one that's the largest side, which I would call the hypotenuse. And this guy has to be the adjacent side of the triangle, right? And without spending too much effort, I can then set up the sine and cosine relationship. The sine of theta is just opposite over hypotenuse. So we can write sine of theta is opposite, which is FG parallel, over the hypotenuse, which is FG. Right? And if I times both sides by FG cancels out, we get FG parallel is equal to FG sine theta. Right? This is a key relationship. Now it connects the amount of push down the incline, how steep, to make the incline. Right? And we do the same thing with cosine, right? I did with sine, might as well do a cosine. So we could write cosine of theta is the adjacent side over the hypotenuse. And so the cosine of theta is the adjacent side. We said the adjacent side was FG perpendicular, divided by the hypotenuse, which is just FG. Again, same thing, times both sides by FG, we get FG perpendicular is equal to FG cosine theta. Right, that's our perpendicular guy. And that's our parallel guy. These two equations are the most important thing about this whole lesson today. Because for one, they're not on the reference table. You won't find them anywhere. The only way you can figure them is either draw all these triangles and figure it out from trigonometry, or just remember, down the incline sine, into the incline deals with cosine. Remember that, that's pretty much the most important thing to remember on that. Yes? Huh? Say it again? Sure. Down the incline is FG sine theta, into the incline is FG cosine theta. Right? And these are the most important things to know, because then it allows us to do practical calculations. Let's say I want to figure out what is the normal force for this block. What is our normal force Fn in this case? Right, so it's going to be our weight. Right, I'm going to get rid of our little. It's going to be our weight Fg times cosine theta, right? So in this case, how do we find weight, by the way? How do you calculate weight, Abhishek? Weight. Sangha? Mg, right? Fg is equal to mg. So we can just write mg cosine theta is going to be equal to the Fg perpendicular, which is equal to Fn. So in this particular case, m was 10 kilograms from our example. Let me say m was 10 kilograms, and theta was 20 degrees. That was from the entry test, right? So we get 10 kilograms times 9.81 newtons per kilogram times the cosine of 20 degrees. So what do we get? What's our normal force? Yeah. 2.18 newtons. Is that correct? Yeah, that sounds like it's about right. And that'll be the same as that'll be our normal force, right? So if you had friction, then you could use that because the normal force will get there. Now, for the down the incline part, if you want to find FG parallel, it's the same concept. It's just going to be this number, which was 98.1 times the sine of 20 degrees. So what's our parallel part? Yeah, because I just took 10 times 9.81, right? Because that's sine theta. $33.55 newtons. Sorry, parallel. So, how do we calculate the acceleration then on the block? What do you think, Leah? What are you? Yeah, net force divided by mass. I already wrote it over here pretty much, right? So it's down the incline force, which was 33.55 newtons divided by the mass, which we said was 10 kilograms, gives us 3.36 meters per second squared. That would be my acceleration out here. Questions, wonders, comments? Sure, down the incline. Positive. In this case, our axes are defined parallel and perpendicular to the incline. So I don't really need to put a direction in this case since my axis is, the positive axis is down the incline, defined that way. So if you wanted to deal with in terms of relative to horizontal, you could work it out. You'd have to just use the angle of the incline. It's going to be, but I'm saying they're all the interior angle, so it'll be the same angle as down the incline and up the incline. Right? Any other questions? No, soak it all in, take it in. It's a lot, but it's not impossible, right? The key things to remember. What are the forces acting on a block on an incline? You've got weight, you've got the normal force. Because the weight does not clearly fit onto the perpendicular and the horizontal axis, which is the motion, we break the weight into two pieces. A parallel piece that's down the incline, and a perpendicular piece that pushes the block into the incline, matching up with the normal force if you assume there's no other force, right? The string throws gets ugly, but in this case, that's it, right? Once I break them up, I can set up a relationship between the angle of the incline and the way the forces are within the triangles to prove that theta is the same as the angle between perpendicular and the gravitational force, the weight. And using just a little bit of trigonometry with the triangles, you can use sine and cosine to get the parallel and the perpendicular force respectively. That's it. Question? Yes. It's the angle between the weight and the perpendicular component of the weight. The forces acting on the incline. We find a relationship between the angle of the incline itself and the weight and the perpendicular. That's the angle that's the same as the incline thing. Well, the two forces that are acting on the block are only weight and the normal force. Remember, these two forces are not new forces. They are just the weight broken into two pieces. Because when we talked about like velocity, right, when I said 40 meters per second, if I find the horizontal velocity, Vx, and I find the vertical velocity, Vy, these are not new velocities. They're the same velocity, just broken into pieces. And so that's what we're doing with the inclined plane. We're taking a single vector and breaking it into two pieces that are equivalent to the original vector.